For this bell work, we're solving an equation. 3x plus 10 equals 32, no problem. We can take this thing and don't need for distribution or combining like terms, but we do see the need for principles of equality. So that's what I'm going to start with right here. If I get this 3x to be by itself, so if I just drop it like this, that'd be good. But if I'm going to do that, I got to get rid of that plus 10. And by get rid of, I mean I'm going to zero that out by subtracting 10. Just if I do it to one side, I must do that to the other side. That's the principle of equality. So now I dropped the 3x, but 10 minus 10 is 0, which is what we would plan. And then 32 minus 10 would be 22. Okay, next, principle of equality is going to force the coefficient of x to be a 1 and not a 3. So I have to take the 3 and change it to a 1 by dividing it by 3. Okay, so 3 divided by 3 is 1. And I take 22 and divide it by 3 as well. Now that's going to be, it's not such an ugly decimal, but it's pretty nasty. So I'm going to change this into a fraction, 22 thirds. Okay, so this should be our solution, but we can check. Okay, so let's go back to the original equation, which is 3x plus 10 equals 32. Now, if this is a true statement, then I should be able to replace the x with the 22 thirds that we just found. Okay. At this point, all I'm doing is checking for truthfulness. Well, 3 times 22 is 22. Then plus the 10 would be 32. So 32 equals 32. That's a true statement. And now that I know it's true, I can box this in with confidence as my solution. Well, here's our objective, 2 objectives for the day. I can simplify an equation with distribution and combining like terms if it needs to be. Because we've seen situations just like the bell work where there was no need for distribution or combining like terms. And then the second objective, I can solve an equation that requires many principles of equality. Just like we saw on the bell work, it required 2 principles of equality. Sometimes we may need 3 or 4 though, and I think today's max will see 3 though. Okay, so take 30 seconds and copy these down, please. So you'll see just like in this review that nothing really new, just like we saw on the bell work 2. Like a solution is a value that should make an equation true, just like we saw on the bell work, okay? So you should be able to take the x, or whatever letter you're using, replace it with a number, and then you should get a true equality out of whatever value that would be after operating with the values that are given. Then we have the distributive property, and we've seen this distributive rainbows kind of stuff. And remember, distribution is multiplication. So that's why we're multiplying A's with B and then A and C after we've done the rainbow thing. Remember, too, that if you get like a negative and a negative being multiplied, that will give us a positive. And we indicate numbers are positive or terms are positive with plus signs. If they are negative, we will indicate those are negative with minus signs. So it's possible you may have a minus between these, or even a minus out here in the front. Then we got combining like terms. For us, really, we only going to have x terms and constants, okay? So if a term has an x in it, you can't combine it with a constant. Remember, constant is just a regular number. And when I say combine, or when we talk about combining like terms, we're really talking about the operations of addition or subtraction. If you're just multiplying or dividing, you can combine whatever you want, okay? But once we get to see addition or subtraction, then that's when we use combining like terms. Also, when we solve equations like this, we generally go in this order. You distribute, then you combine like terms, and then last of all, use principles of equality, okay? So we take addition and subtraction. Remember, we use addition and subtraction to make zeros, okay? And that'll be important to remember today, even when we see equations that may seem pretty large. And then multiplication and division, we used the division principle of equality on the bell work, and we did that not just to make a 1, which we did do, we did make a 1. It's to make the coefficient a 1, okay? So, coefficient. This is kind of the last thing that we do when solving equations, make 1s. So yeah, you got your distribution first. then you'll do some combining like terms, and then you'll make zeros, and then you'll make ones. All right, it's just today, what we're gonna see is you're gonna see x's on both sides of the equal sign, which will require us not just to zero out maybe some constants, but also some x's if it's necessary. So remember, one of the purposes of principles of equality is to isolate the x's. So you cannot have x's on both sides of the equal sign, okay? So yeah, we may have to use the addition or subtraction principles of equality in order to make some of the x terms zeros so that we can make them go away as well. Hopefully, that may not make sense right now, but hopefully we'll see that in some examples that will kind of clarify that for us. Like this one, 2x plus 2 equals x minus 7. We'll go and solve for x, and whatever value we get for x, we'll replace it into the original equation, and it should give us a true statement. Now, we've already replaced x's in equations where it requires multiple x's to be replaced. It's just this is the first time we've seen x's on both sides of the equation. Now, I've said this before, some students may benefit from seeing this as 1x because we are going to have to zero it out. Now, which of the x's should we zero? Because I see I got 2 x's on the left and then I got 1x on the right side of the equal sign. It really doesn't matter, okay? I always just like to keep the biggest one on its side, and like this 2x is bigger than 1x, so I'm going to keep it on the left, but if it were on the right, I could do that too, okay? And it doesn't matter which side you have the x's on. So this means that I need to zero out the 1x, okay, because I don't want x's on both sides of the equal sign. So let's go and get rid of that by subtracting 1x. It's just if I do it to one side, I need to do it the other side. Now, a common mistake while we're getting used to this, and some students say, I'm going to subtract 1x right there. No, you should not be combining it here with 2 because they're not like terms that you should be combining. So don't put it under the plus 2. Put it with another x term, which is the 2x's. So I see I got minus 1x on the right. I got minus 1x on the left. That's the principle of equality. Whatever you do to one side of the equal sign, you got to do the other side, okay? So what is that? 2x minus 1x? That'd give me 1x. Now I still got this plus 2 equals, well, we zeroed out the 1x. That was good. But now I got my minus 7 as well that I need to drop, okay? So we did simplify this with the principle of equality, kind of as planned. But now that I've got my 1x here, no x is on the right, I've only got x on the left, I got to get rid of that plus 2. And by get rid of, I mean zero out. Okay? So I'm going to take that 2 and minus 2. But if I do it to one side, I got to do the other side. This allows me to take my 1x and drop it. Then I got 2 minus 2, which is 0, as planned. And then I got negative 7 minus 2, which is negative 9. Put that in the calculator if you need to. You should get negative 9. Okay? So this should be the solution because in the end, we have a coefficient of x that's 1, and it just equals a number. That should be good. But let's go back to the equation and just check. Okay, so I got my 2x plus 2. This should equal x minus 7, right? But now I'm going to replace the x's that I have in both x's with the x that I found, which was negative 9. Okay. So we're going to check for truthfulness. So here's my question mark above the equal sign. 2 times negative 9 is negative 18. And then plus 2 makes that negative 16. Now, if we get the same thing on the right side, it should be good. Negative 9 minus 7, that's going to be negative 16. Also, this is actually true, which we wanted it to be. Which tells me now I can go back to the solution. 1x equals negative 9. And I know that it makes the equation true. So I know that it is the solution. To be more specific here, I went in, I replaced the x's with the negative 9, and I found it gave me a true statement. That's why it's the solution. Let's try this one though. So now we see not only x's on both sides of the equal sign, but we also see some parentheses for distribution. And in fact, like I said before, we're planning to see some combining like terms as well. So on this one, with my parentheses, I got this set of parentheses, so I'm going to distribute the 6. And like I said, maybe it's good for you to see that as 1x. So I start out, and I got 6 times 1x. Okay, so that would be 6x's. Okay, and the second distribution is 6 times, I would show it as negative 8 because of the minus sign. And that would give me negative 48. Okay, so there's that distribution. All right, fair enough. Let's distribute the 3 into this set of parentheses then. Okay. And again, if you benefit from seeing that as 1x, then show it. You don't have to, but you can. It was there the whole time. It's just lurking in the shadows, right? Remember those are phantom ones? So that would give me 3 times 1x there, which is 3x's. And then also, I got 3 times 7, which is positive 21. Now, in addition to this, so that's all the distribution I have. Make sure not to distribute the 3 to the negative 14 there. But I do have my equal sign, and I still got the minus 14 as well. Okay, so my new equation is 6x minus 48 equals 3x plus 21 minus 14. So that's the distribution. Did it make it smaller? No, it did not make it smaller, but it did simplify it for us. Okay, and there's the difference between the two. But now we're going to make it smaller with combining like terms. So I see on the left side, I got 6x minus 48. Nothing to combine there. They're not like terms. On the right side, I got a 3x and plus 21. Okay, again, these are not like terms. 3 has an x, 21 does not. Now I got this minus 14. And with the 21, though, I got the minus 14. Well, those are combinable, okay, because they are like terms. So 21 minus 14 gives me positive 7. I'm showing the plus sign there because we're going to need it when we write out the rest of it. Okay, so the rest of it, 6x now minus 48 equals 3x plus 7. So instead of showing it as 21 minus 14, we're just showing it as plus 7. That's it. Remember, that's the whole idea with simplifying these. We're not actually changing the overall value of the equation. We're just changing the way that it looks, even if we're narrowing it down into 1x, which is what we are doing, okay? So I don't see any more distribution. I don't see any more combining like terms. This means I can go straight into my principles of equality. So for my principles of equality, I would start looking at my x's. I got 6 x's on the left. I got 3 x's on the right. Okay, again, where is there more x's? More x's on the left. So I'm going to keep those there, which means that the 3 x's, I need those to zero out. Okay, so that all my x's can be isolated. So minus 3x there, but if I do it to one side, principles of equality say I got to do the other side as well. So 6 x's minus 3 x's would leave me with still 3 x's, but now I can drop my negative 48, which equals 3x minus 3x is 0, and now I can drop this 7. Okay, positive 7. I don't need to show the plus because I'm not actually operating with anything else. I'll just keep it like this. Fair enough. But now we're going to use another principle of equality on the negative 48 because, as I've said before, we'd like these 3 x's to be by themselves. Again, that's called isolating the variable. So the negative 48 has to be zeroed out by adding 48. But if you do it to one side, like the left, you have to do it to the other side, like the right. Plus 48. 7 plus 48 is 55. Now we're so close, but we do have one more principle of equality to perform. That is to force the coefficient of x to be a 1. I want this to be 1x, not 3 x's. So how do you make a 3 a 1? Just divide it by itself. Now I'm showing the division a little bit different than I did on those last couple, but we can do it on the right side as well. And you could use the division on that, 55 divided by 3, but with that ugly decimal, I mean, it just repeats. I prefer to see this as an improper fraction, not even a mixed number, just an improper fraction. 55 thirds, this should be true. So let's give ourselves some space here. Let's rewrite the equation that we started with. All right, so over here on the right, I've rewritten the original equation, but now I'm going to go in and I'm going to replace all the x's with the x value that we found and that we think true, should be true. Okay, and that value is 55 thirds. So 55 thirds here, 55 thirds there, because there was only the 2 x's to replace. So at this point, all I'm going to do, so I got my question mark because I don't know if it's true or false. Let's go ahead and put this in the calculator, see what we get, okay? So I type this in, 6, so 6 parentheses, let's see if I can get my calculator, 6 parentheses. I'm using the N over D button, 55 thirds minus 8 close parentheses. Now when I push enter here, I get 62 on the left. Now if I did this right, meaning 55 thirds is the solution, I should get 62 on the right as well. So 3 parentheses, N over D button, 55 thirds, and plus 7, close parentheses, and also minus 14. Now again, before I push the enter button, I'm expecting to see 62. I push it, I see 62. This is true. Okay, so again, since it is true, now I know I can box this in with confidence as my solution. So here's my solution right there. Okay. Definitely more steps to these types of problems, but I mean, really, are they hard steps? I would say no. So with that in mind, you guys try this one out, see how you do. Don't forget your phantom ones, that may help you on this stuff. Try this one out though, take a minute, and then we'll go over it together. All right, so let's see how we did on this. Make this a little bit bigger. All right, now, again, is this super complicated? I don't think so. It's just a matter of just keeping your steps in order and keeping track of them, okay? It's just that there's a lot of steps, so it's just more work, that's it. So, I see some distribution with the parentheses, right? We got this set of parentheses, we got this one. Okay, now this first set of parentheses, some students look at this, they're like, I don't know what the crap to do right here. I don't know what to distribute. It's actually a 1. In fact, it's not even a 1, it's a negative 1 because it takes the operation to its left. And so, again, you may benefit from showing that as 1x, but now I'm showing this as negative 1 times 1x, which would be negative 1x. Okay, and also I got the negative 1 distributed to 5, so that's negative 1 times 5. That's going to be negative 5. So again, since it's a negative, I show it as minus 5. And again, that's as much distribution as is necessary because all distribution is multiplication, but between that parentheses and the 3x is a plus sign, so that's where it ends. Next up, we got this 2 that we need to distribute, but it's not even a 2, it's a negative 2 because of the minus sign on the left. Okay, now between these two, without distributing the negative 2 yet, sometimes that's enough for students to see that they made a mistake, and that's okay, we're just practicing right now, right? But some students miss that phantom 1 that we've shown on the left. Some students forget to make this 2 a negative 2, which it is. So there's 1x as well, so I'm going to distribute this negative 2x's, negative 2 times 1x's, which would be negative 2x's. And then also, over here, with this distribution, we got negative 2 times negative 8. But that's going to be positive 16, so again, I'm showing that as plus 16, okay? So what else do we got? Well, we got the 6, so that's 6 minus 1x minus 5. And then we got this other stuff right here, so that's plus 3x equals 9, minus 2x plus 16, and then we got the rest of that stuff as well, so minus 3x plus 10. Okay, so that's just from the distribution. Does it make it smaller? No, it does not. Does it make it easier to work with? I hope so, because now that we've done that, we are now able to use combining like terms, okay? And there's lots of terms to combine. Now, where is the equal sign? And why do I want to see the equal sign? It's right there. Why do I want to see it right there? Because where the equal sign is important because that's where the combining like terms ends. Okay, you can only combine like terms on each side. You can't start mixing sides because to do that you need principles of equality. So I like to start from left to right, and I say I got a constant there, 6. Are there any other constants on the left side of the equal sign? Sure, 6 and negative 5. So let's go and combine those, 6 and negative 5, which would be positive 1. Are there any other like terms? Yep. Got negative 1x's and 3x's. So that's going to tell me that with negative 1x's and 3x's, that would result in positive 2x's. So again, the positive sign is shown as a plus sign. That's it. Okay, so we took 4 terms on the left, and we've now narrowed that into 2 terms. Okay, the right side has 5 terms, but again, there's only 2 different types of terms, an x term and then a constant term, the regular numbers. So in the end, after combining like terms, I should end up with only 2 terms. So again, I start on the left, I got a 9, the constant, so I'm going to combine all my constants, 9, 16, and 10. When I combine those, I get 35. Okay, well, I got some x's as well, right? So I got negative 2x's and negative 3x's. How many x's is that? Negative 5x's. Okay, so where the distribution did not make the equation smaller, combining like terms definitely did. But now that we've done that, we're ready to use principles of equality because there's no other combining like terms here or distribution. So I'm going to use the principle of equality. Let's start. And so I would start with the x's here. Excuse me. And what do I got? I got 2 x's on the left, I got 5 x's on the right, even though they're negative. So I got more x's on the right, which means that I would want to get rid of that 2x. And by get rid of, I mean make 0. So 2 x's, I'm going to subtract 2 x's. But if I do it to one side, I got to do the other side as well. So that will 0 that out. That allows me to drop my 1, which is isolated now, but I don't care if my constants are isolated. I want the x's isolated. So the 35 can drop as well. But now I got negative 5 x's minus 2 x's, which is negative 7 x's. Okay? So our equation gets even smaller. Now we have only 3 terms. But here, at this point, I want to isolate my negative 7 x's. So the 35, I'm going to have to zero out by subtracting 35. See? And what does this give me? Well, 1 minus 35 would be negative 34. And then this would equal 35 minus 35. That's 0 as planned. And again, I'm dropping this not just as 7x, but it takes the minus sign as its sign. And the last thing I need to do here is to make the coefficient of x a 1. So with a little bit more space, I think we can do that. There we go. So let's see. Take principle of equality, right? Because I'm planning to make this a 1x. But how do you make a negative 7 to 1? Just divide it by itself. Now, instead of showing this as a divide sign like this, like I've been doing, I'm just going to show it a fraction line. Okay, so divide by negative 7 on the right, divide by negative 7 on the left, and this should give me my answer. I'm going to put that in the calculator. I'll keep this as a fraction, 34/7. Okay. Now, as fun as that was, we're not done, because I want to just make sure that I do have a solution. So instead of rewriting the problem, which I was almost planning on doing, I'm just going to go back up here. I'm going to replace this x with 34/7. I'm going to replace this x with 34/7. But it looks like we got a couple more, right, on the right side. So let's replace this x with 34/7. And let's replace this x with 34/7. Okay, well, what does this do? Well, I just want to check to make sure that this gives me a true statement. So let's put a question mark over the equal sign, right? So I put this into the calculator, and when I do, on the left side, I got, let's see, 75/7. Okay, so the left side of the equal sign gives me 75/7. And when I put this into the right side, and again, I'm using the N over D button with the fraction, but I also got 75/7. Now, the last time I checked, that was true, and that's good news, because that tells us that the number that we found is actually the solution. So just to reiterate, that means that if you take the x's and replace them with the 34/7, as we did, you do actually get a true statement. That's why we call this the solution. All right, here we go. Let's do this one. So some distribution, definitely some distribution right here. So I'm going to take my 2, multiply it by the 3 x's, and that'll give me 6 x's. But also 2, again, it's not just 2 times 2, it's 2 times negative 2, which gives me negative 4. So this equals a 20 still. It's good news. But now I'm ready to use some principles of equality, okay? So let's go ahead and start on those. Because, again, why am I using principles of equality now? Well, there's no other distribution or combining like terms. So I'm looking to zero out values. Specifically, that minus 4, I'll add 4 to it to zero that out. But if I do it to one side, I got to do it the other side, right? So that will zero that out, allowing me to drop the 6 x's by themselves. That's called isolating the variable. 20 plus 4 is 24. Last thing I want here is 1 x's, not 6 x's. So how do you make a 6 of 1? Just divide it by itself. And again, I'm showing that with that division with the fraction line. 24 divided by 6 is 4. Well, if we did this right, which I think we did, we should be able to write the original equation, and then if we replace that x with 4, we should get a true statement. Let's check. Okay, so I'm going to take this x, and I'm going to replace it with 4, and I will check for truthfulness. So question mark above the equal sign. And yeah, we do get 20. 3 times 4 is 12, minus 2 is 10. 10 times 2 is 20. So we get 20 on the left side. We already have 20 on the right side. That indicates we have a true statement. If you replace the x with 4, so that's our solution. Here's our two objectives. I can simplify an equation with distribution and combining like terms if it needs to be. Sometimes we see equations that don't have any distribution or combining like terms, just like we saw in the bell work. But if they do, then we should be able to do that, and then also using principles of equality. But now we're using principles of equality not only on constants, but also on x terms also.